Hi, welcome to Unlock Layout and Design, and today we will discuss about multipliers and fingers. First, let's try to understand some transistor fundamentals. Suppose say I have a N MOSFET like this, which has got a width W and L. So then what is the current? ID in saturation is half mu N COX W by L into VGS minus VTH whole square. Suppose I have some VGS and a fixed VDS, okay, so that there is no channel length modulation. Then the current is directly, so this half is a constant, mu1 is a constant, COX is a constant, VGS I am not changing, VTH is constant, VGS I am not changing, so this entire quantity is also a constant. Then the current is dependent only on W and L. Okay, so this is important. So now the current is totally dependent on W by L. So if so, now ID is proportional to W by L. Okay, so ID is proportional to W by L. Rest all are like constant. Suppose if I make W two times. Earlier I had W as 1 micrometer. Now if I make W as 2 micrometer, so how much will be the current? Earlier say when width was 1 micrometer, say 1 microamp was flowing. When width is 2 micrometer, 2 microamp will flow. Okay, so it's directly proportional to the width. Okay, and next question is, suppose now we will come to length. Okay, earlier say length was 1 micrometer. Now I will make length as 2 micrometer. What will happen? ID will reduce by half. Okay, so it is inversely proportional to length and directly proportional to width. So suppose say I have a transistor like this having W by L, and I have one more transistor which is having 2 times W by L, that's nothing but 2W by L. Then if this can carry current of I, this can carry current of 2I. Now if I have one more transistor W by L and I have one more transistor having W by 2L, here length has increased, here width has increased. Okay, so then if this can carry current I, this can carry I by 2. Okay, these are the fundamentals that we should know. So now we'll discuss something known as the fingers and multipliers. Okay, so assume I have a transistor of width W and length L. Throughout this discussion we are not going to change the length of the transistor. Okay, this length will be L only. Okay, so suppose I have the transistor with width W and length L. So this one has got a current carrying capacity I, let's say. So what is the W by L? It is just W by L. I is proportional to W by L. Now I have two transistors. I cut this out across this axis and I have two transistors here. Each one having W by 2. Okay, this one also has got W by 2. Two transistors of W by 2. Okay, now this is the drain. This is the drain, this is the source, this is the drain, this is the source. I will connect this drain with this drain. I will connect this source with this source. I will connect this gate with this gate. So how does it look like? I have one transistor like this and I have one more transistor like this. Drain and drain is connected, source and source is connected, gate and gate is connected. So the current I, each one is having how much? I told you, if W by 2, then I or the current also will get reduced, I by 2. If width decreases, then the current carrying capacity also decreases. So this also can carry I by 2. So here it carries I by 2 and here it carries I by 2. Together what is the current? It is still I. So if this was able to carry I, these two transistors can also carry together, they can also carry I. So this kind of arrangement wherein I split that transistor into two separate drain gate source separately, I have two separate transistors, then it is called as multiplier. It's called multiplier. So when I split this into two and have each one separate, so I have what is known as the multiplier. So multipliers will have separate drain source gate. Okay. So now what I do is, instead of this, I can do one more arrangement. This is gate, this is drain, this is source. Okay, and this one had a width of W. I made this one W by 2. Okay, I have got two transistors of W by 2. This is drain, gate and source. What I do is, for this transistor, I will flip it around so that this becomes drain, this becomes gate and this becomes source. Now this drain I will bring and overlap onto this drain. Okay, so this drain I will superimpose on this drain, and that's what is the structure here. So this is the common drain, one sitting on top of other. This is the source and this is the source. These two are the gates. I will connect these two gates. Drain is already connected, source I have to connect. So I will connect these two sources. Now what is the arrangement? So this is the drain. Okay, so I have two transistors like this. Okay, sources are connected, gates are connected. Drain, is it connected? Yes, it is connected because it is overlapping. This is drain, this is gate, this is source. This one is W by 2, this one is W by 2. They both together will become like equal to W. So this also has an effective width of W, and if this transistor, big transistor, can carry a current I, these two transistors this way can also carry a current I. So it's one at the same, but only advantage I have is my drain is overlapping. Suppose a current I starts flowing from here. This is the drain, correct? So this is the drain, correct? So I starts coming here. How will the current flow? It will go like this half. I by 2 will go like this from drain to source, and I by 2 will go like this from drain to this source. I by 2 and I by 2. Half here and half here. So together I only will flow. So this kind of a arrangement wherein I overlap the drain is called as multi-finger transistor. So I say this is a transistor of width W but having two fingers. Okay, each finger has got a width of W by 2. So here this is a transistor, two multipliers, each having width W by 2 and effective width is W. In this, each one is having width of W by 2, effective width is W, but it has got the drain shared, and that's why it is also called as. So first nomenclature is finger, multi-finger transistor, two finger transistor. Next one is I am sharing the drain, that's why it is called as shared transistor or a shared device. Third nomenclature is also there, that is I had this one is drain and source, and here I am folding it, right? So drain and source I am folding it and then overlapping, that's why it is also called as folded device. So these three nomenclatures, all of them mean the same. Okay, so why should I do this? That's the question, right? So why should I share the drain of the transistor? So we'll answer this question little later, but this is one type of arrangement which is called as multi-finger or folded, or it is also called as shared device. And this, when I have both of them separate, so that time I will call it as multiplier. Okay. So hope this is clear. What is the difference between multiplier and finger? Multiplier will always have two separate transistors, but whereas fingers will have like a shared drain. Okay, one other important configuration that we need to understand is, we know this one is like a width of W, which we split into W by 2 and W by 2. Okay, this one is the drain, this one is gate, this one is source. This one is the drain, this one is gate, this one is source. Okay, so when I do a configuration like this, so what did I do? So I put the drains common and sources on separate. So this together is my source, this is my drain, and then this is my gate. Okay, so now this is a parallel operation. Okay, so I have two transistors which are still connected in parallel because sources are connected, drains are connected, gates are connected. Okay, there is one more configuration possible in this only. Suppose I have drain, gate, source, drain, gate, source. I connect source of this to drain of this, and this my source, ultimate source, and this my ultimate drain. Okay, so now this is the drain, these two are the gates I will short. This, the source of this is connected to drain of this, that is this connection. Okay, and this is my ultimate source. Now what happened here? So let's try to analyze this one. Okay, so now this is the connection actually what happened here. So now a current I by 2 was flowing, correct? So if W by 2, the current carrying capacity is I by 2. If you connect in parallel, then it will have like both of the transistors will have I by 2. Now this current has to go through this transistor which also has a current carrying capacity of I by 2. So now if you see this transistor, now the current started from here, it underwent this channel length, then again it underwent this channel length. So now it became a transistor. So now what is the width? Width is W by 2. And what is the length? Length is also 2 times. So now it became like the transistor, effectively it became like W by 4L. Okay, so now I made these two are in series. So this one, the effective length increased, it became 2L. The transistor length became 2L. So this is a common misunderstanding which we need to be clear. So if this is a drain and this is source and this one I don't take at all, then it is like I am increasing the length of this device. It will become 2 times the length. Okay, and this is the W by 2 width of this device. Whereas I connect this one as a drain and this one and source, and I connect these two sources like this. Take this one as drain, connect these two, then it is like connecting in parallel like this. It's connecting in parallel. So the effective width is 2 times W by 2. So it becomes like W only, and length is still the same. Length is, so the effective width is W by L. Whereas I do other way, like this is the drain, this is the source, and this is the drain of the other device, and this is the source, and I take drain here and source here. Then what happened? The width is W by 2 and length is 2L. Overall W by L is W by 4L. So we will be changing the device by this magnitude. Okay, what was earlier W by L, now it became something like this. Okay, so this is the change, and this kind of connection is done to increase the length in FinFETs actually, or even in normal MOSFETs. If I have two transistors, each one having W by L, and if I want to increase the length, then I will connect them in series like this, and I will connect gates together. This is my drain and this is my source. Now it is W by 2L. Okay, the effective length of this transistor is W by 2L. So this is one connection which we do, but please be aware that this connection is also possible. Now we'll try to understand if this one has got 2W. Instead of W, I have like 2W. What will be the individual transistor size? This one will be like again W and W. Half of this will be W by 2, W by 2. So each one will be W by 2, W by 2, W by 2 and W by 2. Now I have a transistor of 4 multipliers with width W by 2. So now if I multiply 4 into W by 2, what is the effective width? It is 2W. 2W is the width. Okay, so this is clear. So why is this multiplier? See, unless I can connect all the drains, it will not become multiplier. Okay, I connected all the drains like this. Now I have to connect all the sources like this, and I have to connect all the gates like this. So now it is a 4 multiplier arrangement. Okay, so a width 2W now got into 4 multipliers, each one having W by 2. Now again same thing, each one is W by 2, W by 2, W by 2, W by 2. So overall what is the width of this? It is 2W. Okay, now I have made this into like how many fingers? Like 4 fingers. Okay, each one, this one is drain, gate, source, first transistor. This is drain, this is drain, this is gate, this is source, second transistor. Okay, this is drain, this is gate, this is source, third transistor. This is drain, this is gate, this is source, fourth transistor. How many gates are there? So many transistors are there. What is the width of each transistor? It is W by 2. So it is 4 into W by 2. So that is nothing but 2W. Okay. So now I have 4 fingers here. 4 fingers. Okay. So here how many things I have shared? This is source. Okay. Now we will do this is source, this is drain, this is source, this is drain, this is source. So I have got 2 drains and 3 sources. I have to connect all three sources like this and 2 drains like this. This is my drain, this is my source, and all the gates I will connect like this. This is my gate. So this is like 4 fingers. Earlier we saw 4 multipliers. In this we saw like 4 multipliers. In this we see 4 fingers. Both of them are the same. Okay, means the same 2W width of transistor 2W. I have done different connections with fingers and multipliers. So now I have like 4 transistors of W by 2. Okay, so which was like integrally it is 2W. I have made that into 4 W by 2, W by 2, W by 2, W by 2. Okay, so 4 transistors. What I made is this one is a 2-finger transistor. And I took out of these 2 I made this transistor, out of these 2 I made this transistor. Again this is 2-finger. So now this one is 1 multiplier and this one is 1 more multiplier. So now I have 2 multipliers. So this one, now this one is 2-finger, this one is 2-finger, this one, these 2 are 2 multipliers. So together I have 2 multiplier and 2 multiplier and how many fingers? 2 each. Each one has got 2 fingers. Okay. So this is the arrangement. Now 4 transistors. I have 2 here and 2 here. I have 2 multipliers. Each multiplier has got 2 fingers. So overall it is like 4 transistors of W by 2. So this is one more arrangement. Okay. So first and foremost question is, why should I have multi-finger transistor? So I have this one as a drain, source, and this one again as drain and source. If you see Now I am overlapping the drain here. I have a common drain and two different sources. Now if I have earlier, we saw in the previous video, we saw what is the, see, if I have a transistor like this, I have drain to bulk capacitance like this, CDB. Okay, so CDB, that's what we are revisiting again. So if you see, this is the drain N plus region. So this one is having now the length of that one is E, and what is the width of this guy? That is the width of the transistor itself. That is the width. Okay, now what am I doing? I am actually cutting this into two parts. Okay, what is the capacitance? Bottom plate capacitance, which is the big capacitance? E into W into the unit capacitance Cj. That is the capacitance of this entire bottom plate surface. Okay, now when I cut this into two, parts, each part will have how much capacitance? Cj is the junction capacitance into W by 2 into, this is E only still. So this portion is W by 2. This portion is W by 2. So each one will have W by 2 into E. Now, so this one, each one will have half of the bottom plate capacitance. Okay, or the junction capacitance Cj is now half. Each one will have half of them. Each drain will have half. This one will have half. Cj, which is nothing but W by 2 into E. Okay, so that's why it will be half of the junction capacitance. Okay, hope this is clear. So the capacitance, the junction capacitance of the drain is half. This one is also half. This one is also source also half. Source also half. Okay. Now what I do is I will overlap these two into a single drain. So what happens to the area of the drain? Area of the drain is half. So what happens to the junction capacitance at the drain? Drain junction capacitance is now half. Okay. Whereas I have two sources still. For source I have half, but I have two of them. 2 into half capacitance will again become 1. So source capacitance is not altered, but the drain capacitance is altered. So that is the biggest advantage I get when I share the devices, by sharing the junction capacitance of drain or the whichever is shared. If source is shared, source capacitance will reduce. That will reduce, which is a big advantage. So what I have written down here is nothing but the common source amplifier. Okay, so what I have written here is nothing but the CDB, which is nothing but the drain to bulk capacitance. We saw the drain region, and to the bulk I have a reverse biased junction, and in between I have depletion region. So that acts like a capacitance insulator, and this is N and this is P. In between I have this capacitance. That drain bulk capacitance has become now half. So in order to understand the complete capacitance, you look into the MOSFET capacitance video. In that it is discussed in detail. So here I have a reduced drain bulk if I have multi-finger. So what is the use of this one? So suppose say I have this one, I am using it as a amplifier. Okay, and then we know this XC, this capacitance Xc is equal to 1 by 2 pi F into C drain bulk, whatever is there here, CDB. Means what? This impedance will decrease with increase in frequency. Okay, if frequency increases or this capacitance increases, then this Xc will decrease. If capacitance will increase, then this impedance decreases. That means Vout is connecting more and more towards ground. That means if this is very low, then Vout and ground is connected to ground even for lower frequency, means output is 0. Okay, and if it is lesser, this capacitance is lesser, then what happens? If output voltage is higher, and then it will be like this. Okay, so if capacitance is big, it will reduce the output voltage. What is happening to my gain? Gain is becoming 0 at very low frequency. So that's why I don't want this capacitance to be big. So if the capacitance is big, then my bandwidth will be lesser. So even for a small frequency, this will become like a short circuit from output to 0. Then I will not get gain. This is the gain at lower frequency. Okay. So as and when the frequency increases, what happens? This becomes like short circuit to ground. So that's when the gain will fall and output will become a 0. If this capacitance is very small, then it will be like this. So at a higher frequency, it starts going to 0. So then my bandwidth will increase. Okay. So if I have like a big capacitor, then it will be something like this. And if I have a small capacitance, then it will at higher frequency, it will start going to 0. So now what is this? This is nothing but my bandwidth. This is frequency, this frequency, this is the amplitude gain. So here bandwidth is lesser, here the bandwidth is higher. So if this drain bulk capacitance decreases, the bandwidth will be higher. So I can operate my circuit at a higher speed. That's the advantage. So first we'll also try to understand why I need fingers and multipliers. See, now I have a very big transistor. Say this itself is a very big transistor. So how does it look like? It looks like a rectangle. Okay. I don't want my layout to look like a rectangle because my matching will be poor. So for that reason, what I do is I will split this into two transistors and two fingers. Now I make it like this. Now it looks like a square. This entire thing looks like a square. From matching perspective, it is very good to have like multipliers and fingers both. So if you have multipliers, you can place them in many rows. If you have fingers, you can share the drains. So which is the advantage for sharing. By sharing, you are not only reducing capacitance, you are also reducing the area, and also your matching is also much better. So that is the advantage of fingers and multipliers. Okay, here I have 2W by L and here I have 10W by L. So now what is the current carrying capacity? So 2 times 2W and here it is 10W. 10W by 2W, which is 5 times. So here if it is 1 microamp, here it will be 5 microamp. Got it? Okay, so this 2W will be like two fingers. Okay, so I can have each one as width of W and I have two fingers, and this one will have like 10 fingers, each one having W. Okay, like this only it will have like 10 fingers. So how do you get the fingers? So many gates would be there. Okay, so we'll speak about more about fingers and multipliers during current mirrors, which we will discuss later. In that we will speak about fingers and multipliers, matching, all those things. So this is an introductory video about fingers and multipliers. Okay, let's summarize whatever we discussed. So multi-finger transistors are used to reduce parasitic capacitance. That's the main advantage. And it is also called as folded transistor, shared transistor. Okay. So multi-finger transistor, folded transistor, shared transistor, all of them mean the same. By reducing the parasitic drain capacitance, bandwidth or the speed of the amplifier increases. It also improves in matching. It reduces the area and also helps in matching. And multipliers are required when transistor size is big, okay, and have to be placed in multiple rows to form a square shape to achieve common centroid matching. So better matching or two-dimension matching can be achieved by having more multipliers and fingers. So that's the advantage of having multipliers and fingers. So hope you enjoyed the video, and please hit the like button and don't forget to share and subscribe.